Welcome to the Mental Minute, an AI-generated podcast. Today, we're going to do a deep dive into something pretty unexpected, I think, Benford's Law.
Interesting.
Have you heard of this before?
I have actually.
Okay.
Yeah, it's also called the law of anomalous numbers, or the first digit law.
Right. And the thing that's so fascinating about this is that, you would think
Mm.
if you just look at, the digits 1 through 9,
Yeah.
you'd expect each of them to show up as the first digit about, 11% of the time.
Uh-huh.
Like it should be a pretty even distribution.
Right. Makes sense.
But Benford's Law says no.
Yeah, it says
It says 1 is way more common.
way more common. Yeah, you're talking about like 30% of the time you'll see the digit 1 as the leading digit.
Wow.
And then 9 is way less common, like less than 5% of the time.
That's wild.
Yeah, it's really counterintuitive.
It is. And it's not just about the first digit.
No.
This law actually, it goes on and making predictions about the second digit and the third digit.
Yeah, you can generalize it.
And so on.
Yeah, and what's even more interesting is there's like this statistical relationship between those digits.
Really?
Like they're not totally independent of each other.
So there's a pattern there.
There's a pattern. There's a hidden structure in the numbers themselves.
So this is making me think, like, is this just like a quirk of our decimal system?
Right. You would think that maybe
Yeah.
it's just because we use base 10.
Yeah.
But the amazing thing is
Yeah.
this pattern holds up even if you switch to a different number base.
Really?
Like if you're counting in twos like a computer does or any other base,
Wow.
the underlying tendency stays the same.
So this is not...
It's not a superficial mathematical trick.
No.
It's something deeper about how these data sets are actually generated.
Okay, so prepare to have your mind blown a little bit.
Okay.
This law pops up in the most random places.
Yeah, where does it show up?
Like your electricity bills.
Hmm.
The numbers on street addresses.
Okay.
How stock prices fluctuate.
Interesting.
The populations of cities.
Wow.
The lengths of rivers.
Right.
Even fundamental constants in physics.
It's really remarkable how this pattern crosses all these different fields.
Yeah, like what is connecting the flow of electricity with the stock market?
Right. It makes you wonder what kind of underlying mechanisms could be at play here.
So, okay, let's try to understand like why this happens.
Okay.
At least in some cases.
Yeah.
Part of it has to do with data that spans like a really huge range, like multiple orders of magnitude.
Right. So think about those populations you were talking about.
Yeah.
Like a small village might have a few hundred people.
Yeah,
A big city could have millions.
exactly.
That vast scale, that allows Benford's law to kind of emerge.
Okay, so when data covers that much ground,
Mm-hmm.
that's when you start to see this.
Yeah. And also, if the numbers in a data set tend to grow or shrink by multiplication
Right.
rather than addition or subtraction,
Okay.
you're more likely to see this pattern as well.
But here's the thing, and this is where I think that name the law of anomalous numbers comes in.
Uh-huh.
There are times when this law applies,
Yeah.
and we don't really have a good explanation for it.
Right. It's like the numbers have this secret preference, and we don't know why.
Yeah.
It's a mystery.
Yeah.
It challenges our idea that all digits should be equally likely.
Right.
It suggests this kind of inherent bias in a lot of numbers.
Interesting. So what does this mean for like the average person?
Okay, so one really important application is in detecting anomalies,
Okay.
like errors or even fraud,
Okay.
especially in financial records
Oh, interesting.
and economic data.
So like
The idea is if someone is cooking the books,
Mm-hmm.
they'll often subconsciously create a more uniform distribution of first digits.
Okay.
They'll try to make it look random, but they'll mess it up.
Right.
So if a data set deviates a lot from what Benford's law predicts,
Mm-hmm.
that can be a red flag.
That's so cool.
Yeah, it's like a statistical alarm bell.
So you might have heard about this being used in like criminal trials.
Yes.
Or to analyze election data.
Right. But that's where things get a little tricky.
Okay.
Applying Benford's law to elections is very controversial.
Okay.
And it's really important to understand the specifics of the data you're looking at.
So like what kind of things do we need to keep in mind?
Well, if you have a data set with inherent constraints,
Right.
like vote counts within a small precinct,
Okay.
where the total number of votes can't vary that much,
Right.
Benford's law might not apply,
Right.
and you could get misleading results.
So it's not a silver bullet?
No, definitely not. You need that wide range of values for it to work properly.
Gotcha. But beyond fraud detection, there's some really cool uses for this.
Absolutely.
Like I've heard that researchers have used it to study patterns in macroeconomic data
Yes.
and even to look at things like genome sequences.
Yeah, it's even been used to study how researchers collaborate.
It's amazing. So it's not just about catching criminals.
No, not at all.
It's got a lot of applications.
It has a lot of potential in different fields.
But it's important to remember,
Mm-hmm.
not all data follows this law.
Right,
It's
exactly.
like if you've got a sequence of assigned numbers, like your check number,
Yeah, or invoice numbers.
you wouldn't expect those to follow Benford's law.
Right, they're not generated in the same way.
And what about data that's like heavily influenced by human psychology?
Yeah, like those prices that end in 99 cents,
Yeah.
those tend to deviate from the pattern too.
So there are exceptions.
There are definitely exceptions. It's not a universal rule.
Gotcha. So what about like a data set with built-in limits,
Right.
like a clear minimum or maximum value?
Yeah, good point.
Or if the numbers don't really span that wide of a range,
Mm-hmm.
like human heights,
Yeah.
everyone's kind of in the same.
Right, we're all roughly the same height.
Yeah.
Benford's law typically won't apply in those cases.
Okay, so let's get a little bit mathy here.
Okay.
Like, how does this work from a mathematical perspective?
Yeah. So one way to think about it is that the logarithms of the numbers
Okay.
in a Benford-compliant data set tend to be more evenly distributed
Okay.
than the numbers themselves.
Interesting.
Also, as we talked about, multiplicative processes often lead to this distribution,
Uh-huh.
while additive ones usually don't.
Okay.
And another interesting thing is even mixing data from different distributions can sometimes create a Benford-like pattern.
Really?
Yeah, it's a pretty robust phenomenon.
So here's something else that I find really fascinating about this.
Okay, what's that?
This thing called scale invariance.
Oh, yeah.
So imagine you've got a list of like river lengths, and you could measure those in miles or kilometers.
Right.
Doesn't really matter.
Yeah, the distribution of those first digits
Yeah.
will likely stay similar as long as you have a good mix of river lengths.
So the pattern is not tied to how we measure it.
It's a property of the underlying data itself.
That's really cool. So I guess the takeaway here is
Mm-hmm.
those seemingly random numbers that we see every day
Yeah.
often have these hidden, elegant patterns.
It's true.
And Benford's law is just one example of that.
It makes you wonder what other surprising laws might be out there.
Right. What else is hidden in the data that we see all the time?
Yeah, what other secrets are waiting to be discovered?
That's a great question.